Good day, grade 12s. I'm Sonnekus, and for this part of the STEM in Action Boost series, we're going to look at verifying the conservation of linear momentum. So, let's go back to grade 10 a little bit, and we look at the scientific process. Scientific process tells me that we need to have a question. So my question for this experiment is, when objects collide, is the momentum of the system before the collision the same as the momentum of the system after the collision? We all remember from the scientific process, if we have a question, we need to set up a hypothesis, okay? And this hypothesis is going to be three hypotheses because we're going to do three different types of collisions: an elastic collision, an inelastic collision, and an explosion. Not the explosion where bombs is going to go off, but the explosion between the two cars. Okay, so when we do a hypothesis, we need to say that what we expect. It doesn't have to be true, okay? It doesn't have to be accurate, word for word or anything, because we want to go and test it, okay? So in this case, my three hypotheses are made up for this. For elastic collision is that momentum is going to be conserved, and for inelastic, momentum is also going to be conserved, and then for momentum, that momentum is conserved. So basically for this three different hypotheses is that momentum is going to be conserved for every single collision. So the materials that we are using for this experiment is the Pasco motion sensors. I've got two of them at each of the end of the track. When working with a motion sensor, we must just make sure that this motion sensor is horizontal. We want to face the back of the car. If it's sitting at an angle, we're going to work in this plane, and we want to work in the horizontal plane. So just make sure that it's horizontal. You'll see on the side there's a gradation, like a setting, so you can just put it on 0 and 180. It'll tell me it's nice and horizontal, and you do the same over here. We have two settings on the motion sensor: a man that walks and the cart, and you just have to make sure that both sensors are on the same setting for the carts. Okay. Then we have the Pasco dynamics track as well as two cars, dynamic carts. A red one and a blue one, just to distinguish between the two. And then I also got to also have a mass bar of 250 grams. Then I'm using the Pasco capstone data software to capture the motion of the cars. So steps: we need to connect the motion sensor onto the system. That's already been done, all plugged in, nice and neat for me. We must make sure that the sensors are all horizontal so that they're facing the cars and not any pointing to weird and wonderful directions. And then we need to go and find the masses of each car, because we need to add it into this table. Okay, so I've got my table over here, and I want to populate this with the data that I'm collecting. So we're going to take the mass of the red car, place it on a balance, and we're going to see that there's the red car that is 254.24 grams. We're going to take the red car off, and we're going to put the blue car on there with its mass bar, and we're going to see that is going to be 505.37 grams. Okay. Then we need to convert this to kilograms, and you're going to see that this is going to be 0.505 kilograms and 0.244 kilograms. That is the mass, and then we're going to set up the experiment. So for the elastic collision, we're going to start with a cart in the middle of the track. So this is going to be my blue cart. I'm going to place it in the middle of the car. Remember the mass bar for that. And I'm going to take the red car and I'm going to put it onto the side. Not against the sensor, but slightly away from the sensor so that it just picks up the cart a little bit easier. It's difficult for it to track when the sensor is very close to that. When you're working with the cars, you'll see that there's a magnet between the two cars. So the magnet is facing. So if you push it, you'll see it pushes the other car away. So there's a magnet in there, and the other side you'll see there is Velcro strips there, and when they go and they all stick together. So for this part of the experiment, for the elastic collision, you're going to have the magnets facing one another. So we want an elastic collision. Okay, so I'm going to set up my experiment like this, and then I'm going to get ask somebody to help me drive it. I'm just going to assist me with this. I'm just going to need to stop the car for me before it hits the sensor. Okay, so for this, I'm going to just press record. I'm going to wait 3 seconds. So what I'm going to do now is just going to press record, wait 3 seconds, and gently push the red car towards the blue car. Okay, from there we have our graph. So now we need to go and determine the initial velocity before the collision and the initial velocity after the collision. Okay, so when we look at our graph over here, it's like, where's my initial velocity is going to be? So it's going to be over this point over here, this point over there, or somewhere over here. It's going to be at this point. Okay, this is where's the collision happening? The collision is happening over here. Okay, so this is the collision between the cars. So we're going to take our initial velocity, not somewhere over here, okay, because here we're just waiting for the experiment to settle. Okay, so both cars were standing still. Here we just pushed the car, so it accelerated, and you can see that the velocity here is getting constant. So we know the car is moving over there. So just before the collision, so basically at that point over there, that's going to be our initial velocity. The same with the collision. The initial velocity is going to be over here. But what's the initial velocity going to be of the blue car? Okay, that's going to be 0. So now I can know that this red graph over here, that's going to be my blue car. All the green values we're going to record is for the red car, and all the values we're going to record from the red graph is going to be for the blue car. Very confusing, but we need to keep head about this. Okay, so let's look at the initial velocity. I'm just going to grab my tool over here, my coordinate tool, just add my coordinate tool over here, and I'm going to look at that data point over there. So the first value, that's my x value, that is time. We're not interested in time at the moment. I'm looking at my velocity, and we're going to see that there's going to be 0.51, and as green is the red car. So this is going to be 0.51 meters per second. Okay, and for the red car, or the blue car, we know that it's going to be 0, because it was stationary. Okay, if you don't believe me, I can just move this down and go and put it there, and you will see that it's going to be 0 meters per second. Okay, a very small number. Okay, my final velocity is not going to be over here somewhere. It's just going to be that data point or just after the collision. So my final velocity for my red car is going to be, let's take this point over here, and you can see that there's negative 0.16 meters per second. For the blue car, that's going to be 0.34 meters per second. Okay, so now what we need to do is we just need to convert to calculate momentum, and momentum we know it's P equals mass times velocity. Okay, so this is going to be my mass, this is going to be V, and this is going to be P. So you're going to go, and remember we're working with momentum, so it needs to be in kilograms. That is why we converted earlier from grams to kilograms. You're going to multiply my velocity by momentum. The velocity is 0, so we're going to now see that it's going to be 0. And so the total momentum before is 0, that's going to be 0.124 kilograms per meter per second. That's going to be 0.505. Multiply that by 0.34. That is equal to 0.17. Okay, so you're going to go 0. So you just go 0.17 minus 0.039 and it's going to give me a value of 0.131 kilograms per meter per second. So let's go and take these values, so just round them off, so you can see that's going to be 0.1, and round this also off, and that's going to be 0.1, and we see that they are the same, so you can say that momentum is conserved. Okay, so let's go and do inelastic collisions. Okay, so for inelastic collisions, we're going to use basically a very similar setup, but the only thing we're going to do is we're going to change and turn the cars around so that the red car, as the Velcro, is sticking to one another. Okay. Just before I go and do that, I just want to let you guys listen to this noise over here. Okay. Because some part of momentum is we have to look at kinetic energy. Okay. And we also have to determine whether kinetic energy is conserved or not. Okay. So when I go and I push this car to the other side, do you hear something happening over there? I'll do that again for you. So just listen to that noise. Do you hear that? Okay. So I'll come back to that. So just keep that in your mind. Okay. So I could turn this car around, turn this car around, so that the Velcro is facing one another. Okay. So basically the cars will get stuck together. Okay. Now, let me quickly do this again. Do you hear that bang? Okay. I'll talk about that just in a little while. Okay, so for linear momentum, I'm just going to do, Clive is going to grab this to stop the car again just for me, so we just don't bump the sensor. I'm going to press record, wait 3 seconds, and gently push the red car towards the blue car. And I'm just going to stop it over there. Okay, so now I've got my data collected. So now let's look at this graph over here. We'll see that the cars were stationary over here. Around 3 seconds we pushed the car and pushed the red car, and it was moving. So we can see again that the green is going to be the red car and the red is going to represent the blue car. Okay, so where's the collision happening? Okay, the collision is happening over here. Okay, so the same thing again. My initial velocity is going to be there, initial velocity is going to be there, and my final velocity is going to be over there. Okay, so red car or the blue car, let's start with the blue car. The initial velocity was 0, was stationary. And the initial velocity for the red car was 0.55 meters per second. So we're going to multiply those out. So this is going to be 0, and that's going to be 0.244. Multiply that by 0.55. That's going to be an answer of 0.13 kilograms per meter per second. Okay, so let's go and calculate the final velocity. And we'll see that because the cars got stuck together, their final velocity is going to be same because they moved together. If I move this one, the blue one follows it. If I move that one, it follows it. So they got stuck together. So the velocity is going to be exactly the same. So we're going to look at this and grab my tool over here. We're going to move it down over there. And just want to make sure that's a nice point. And we see that the velocity there is 0.18 meters per second and 0.18 meters per second. Okay, so just work out momentum. That is 0.505 multiplied by 0.18. That's going to give me 0.09. And then for card 2, the red card, we're going to go 0.244, multiply that by 0.18. It's going to give me 0.05. 0.4. We just add the two together, so it's 0.9 plus 0.04, and that is going to give me 0.13 kilogram meter per second. So now we can go and ask the question, does the conservation of linear momentum apply for an inelastic collision? And we can say yes, because 0.3 and 0.3 as the same answer, so you can say that is going to be a definitely yes. Okay, so just coming back to that noise, okay, so we know from the previous series and from learning from class that when we deal with elastic and inelastic collisions, that kinetic energy is conserved, okay? So when we listen to that noise and we don't hear anything, we're going to see that with elastic collisions, kinetic energy is conserved. But the moment we have an inelastic collision and you hear this banging noise, it tells me that there's energy being released in the form of sound. So we're losing kinetic energy. So we can say with elastic collisions that momentum is conserved as well as kinetic energy. With inelastic collisions, momentum is conserved, but kinetic energy is not. Okay, so let's move on to explosions. For explosions, I'm going to follow this setup, and basically the car is going to be standing in the center. I'm just going to turn them around. There's a plunger. Okay, there's a big plunger over there. I'm just going to set the red car to a setting over there, and we're going to place them together in the center like that. Okay, then Climate, my trusty assistant, I'm just going to come here and he's going to press that while I'm working on the computer, and you will see the explosion happening over there. So let's just get the data correct on the computer. We delete this, run over here, and we have a nice fresh screen. So I'm going to follow the same principle. Press record, wait 3 seconds, and do the explosion. Ready? So 3 record, that's 1, 2, 3. And we'll see there is our explosion. You'll see that there's 0.505 kilograms and 0.244. And we're going to look at the initial velocity. Well, just looking at it and just thinking about the experiment, what do you think the initial velocity of the red car is going to be, and what is the initial velocity is going to be of the blue car? It's going to be 0, because both cars were stationary. So let's go look at the graph, and we'll see where's the explosion happening. You can see it's over here, because they were still stationary, and then suddenly the two cars moved away from one another. Okay, we'll see that this is going to be my initial point of the explosion. You see that there's going to be 0. So that's going to be 0 and 0, because they were together. So my momentum there is going to be 0 and 0. 0.5 times 0, 0. And so you can see that's going to be 0. So now we have the total momentum before the explosion. So we need to go and calculate the total momentum after the explosion. We're just going to go over here. We're going to grab the coordinate 2 over here. We're going to move to the blue car over here, and we're going to see that that value is going to be, let's move it over there, 0.35 meters per second. And then we're going to move to the red car, which is green over here. I'm going to use that point over there, and that is negative 0.52 meters per second. Let's quickly grab the calculator over here to do the calculation. 0.505, multiply that by 0.35, and we get an answer of 0.176 kilogram meter per second. Okay, so you're going to go 0. Let's calculate the momentum for the red car. That is 0.244 multiplied by negative 0.52 is going to give me an answer of negative 0.126. Okay, so we go 0.176 minus 0.126, and that's going to give me an answer of 0.05. And we can see that answer is very close together, so it's a very small difference between the answer. You can say, ask the same question, with the explosion, is momentum conserved? And you can say yes. So with the explosion, you heard that the banging noise coming out when the cars were separating. That tells me as well that kinetic energy is lost. Okay, so it's just been transferred into sound energy. And ladies and gents, that brings me to the end of the conservation of momentum.